In this video, we'll understand how developers can fine-tune large language models more efficiently using NVIDIA, NeMo, and LoRa. We'll keep it practical, using a retail customer service use case and break down the core ideas step by step so the workflow feels approachable. Large language models are already very capable, but out of the box they are still general-purpose systems. In real products like retail customer support, we often need the model to respond in a domain-specific way, follow company policies, and understand the style of customer queries. That is where fine-tuning becomes useful. It helps the model perform better for a specific business need instead of staying fully generic. From a developer's point of view, fine-tuning is not only about theory. It is about setting up the environment correctly, choosing the right framework, preparing the data, and making sure the training approach is efficient enough to run in the available compute budget. In this article's context, the retail customer service use case gives a concrete direction for how the model should be adapted. Traditional fine-tuning usually means updating all the model weights. For modern LLMs, that can mean millions or even billions of parameters. Naturally, this requires a lot of GPU memory, compute time, and storage for checkpoints. For many teams, especially when experimenting quickly, full fine-tuning becomes too expensive and inefficient. Parameter-efficient fine-tuning, or PEFT, is a family of methods designed to reduce the cost of adapting large models. The main idea is simple. Instead of changing everything, train only a small number of additional parameters. This makes experimentation lighter, faster, and more practical, while still allowing the model to learn task-specific behavior. Now that we've covered fine-tuning basics, let's test what we've learned so far. Here's quiz number 1. See if you can get it right. Question 1. Why do developers fine-tune an LLM for a business use case? The correct answer is to adapt it to domain-specific needs. Fine-tuning helps a general-purpose model perform better for a specific task or domain, such as retail customer service. Question 2. What is a major drawback of full fine-tuning? The correct answer is, it is expensive in compute and storage. Full fine-tuning updates all model weights, which can be very costly for large models. Question 3. What does PEFT aim to do? The correct answer is, train fewer parameters efficiently. PEFT methods reduce the cost of adaptation by training a much smaller set of parameters. LoRa, which stands for low-rank adaptation, is one of the most popular PEFT techniques. Instead of updating the original model weights directly, LoRa freezes the base model and adds small trainable adapter layers. These adapters learn the task-specific changes while the main model remains untouched. This is what makes LoRa much more efficient than full fine-tuning. A useful way to understand LoRa is to think of a transformer weight as a very large matrix that maps input features to output features. Normally, fine-tuning would modify this whole matrix. LoRa says, instead of changing the full matrix, let us represent the update as the product of two much smaller matrices. This gives a compact low-rank update that still captures meaningful task-specific learning. Because the two LoRa matrices are much smaller than the original weight matrix, the number of trainable parameters drops sharply. That means less memory usage, lower computation, and easier storage of fine-tuned components. For developers, this is a big advantage because it makes iteration faster and more affordable without losing the benefits of customization. NVIDIA NeMo is the framework used in this practical guide. It helps developers work with large language model training and fine-tuning workflows in a more structured way. In a hands-on project, NeMo can support the setup needed to experiment with approaches like LoRa and apply them to real-world scenarios such as customer support systems. Now that we've covered LoRa concept, let's test what we've learned so far. Here's quiz number 2. See if you can get it right. Question 1. What happens to the base model weights in LoRa? The correct answer is, they are frozen. LoRa keeps the original model weights fixed and trains only small adapter components. Question 2. How does LoRa represent model updates? The correct answer is by using two smaller matrices. LoRa approximates the update with the low-rank decomposition using two small matrices. Question 3. Why is LoRa considered efficient? The correct answer is it trains fewer parameters with lower compute. LoRa reduces the number of trainable parameters, which lowers memory and compute requirements. That's the foundation of fine-tuning LLMs with NVIDIA NeMo and LoRa. In the next step, you would typically move into environment setup, data preparation, and actual implementation. If this made the concept clearer, you're already in a strong position to explore the hands-on workflow confidently.